big pleasure to be here. It's always nice to come to Bonn. So the reason for this talk is a joint project which certainly many of you have heard of with two physicists, one from this series here, Tokyo, but from series, must be somewhere, yeah, and the other is actually Zagier, and I was going to talk in more detail about that. But since I have to choose among many topics, and since there are many talks today connected somehow with modular forms, I thought I would really give an introductory lecture and explain many of the things, and then mention some of the applications of physics, including ours, more briefly, but emphasizing mathematical aspects rather than the physical ones. I'll say something to try and browse. So, again, I'm a mathematician, so I use the board to define things. I'm sorry for that a lot of people certainly know many of the definitions. That's I claim that I know how this works after 30 years of experience. It wasn't quite true. So perhaps I begin with usual modular forms, since my talk is about modular forms. So certainly I think everybody knows what modular forms are, but I'll review very briefly. Also, I need some examples and notations for everything later. So roughly, we have another little box here. This is the box. I'm going to have the variable tau. Whenever I write tau, it's in the complex upper half plane. Q is e tau, which means e to 2 pi I tau. And later there will be a second variable, which is a complex number, and the corresponding number. And mathematicians are not used to this, but this is usually called a y, and I'll be calling it a y. And when I absolutely need the real and imaginary parts, I'll use this careful physicist notation tau1 and tau2, because of course lots of things have indices that aren't real and imaginary parts, but tau2 will only be that. So this is just some notation. So a usual modular form, the classical modular form, is a function in the upper half plane, holomorphic, which satisfies the equation that certainly everybody has seen, f of a tau plus b over c tau plus d is equal to c tau plus d to some power. This power is called the rate. It's usually an integer, but can also be half integer. Times f of tau. And this is true for all matrices A, B, C, D in the full modular group, SL2Z, or the subgroup with finite index. Of course, much more general definitions, but that's certainly good enough for now. So, we did not explain K, or sometimes I can specify the group. And K is the space of these modular forms, but actually there's a slight question about growth conditions. I'll come to that in a second. But then we start with examples and applications. So if I write some group like SL2Z and I take the holomorphic modular forms, which just means strongly holomorphic, so this is plus a growth condition that I haven't yet set, I'll say in a moment, then this is finite dimensional. And as a result of that, the theory is extremely powerful, because if you have any collection of modular forms, you can prove identities among them, and therefore you get lots of interesting number theory. The theorems more or less for free. So this is kind of classically one reason why modular forms are so popular. But let me emphasize that there are very few. So far as I know, there are basically only 3 classical ways to construct modular forms explicitly. And whereas as we'll see for most modular forms, which is much newer theory, there are actually more. I'll describe perhaps 6. So here I'll number them 1, 2, and 3. So one would be the Eisenstein series. Again, I think most people have seen the definition. I'll just give you the first example. E4 of tau, I always write it, is 1 plus 240 times the sum d from 1 to infinity, d cubed, q to the d over 1 minus q to the d, where q, again, is e to the 2 pi I tau. And so you can write this out as a Fourier expansion, where you have the sum over n greater than or equal to 0 of q to the n times the coefficient. The 0th coefficient is 1, and the general coefficient is 240 times the sum of the cubes of the divisors of n. And similarly, E6 is exactly similar with the 5th powers. And these things are known to be modular forms on SL2Z, and in fact, even more is known if you take 1 modular forms on SL2Z that forms of course a great ring, and it's freely generated by E486. So that's already a bunch of examples. But now you see already that thing tells us identities. So this, maybe I'll take a different color, then it might be hard to erase later. Identities. So for instance, a typical identity, you can define E8 exactly the same way, and then because the space of multiforms of weight 8 here is one dimension, you get for free that E8 is equal to squared, and that implies an identity for sums of 7th powers of divisible number in terms of sums of cubes of divisible numbers, so that's certainly not this identity. So, okay, so that's the first type of example. The second type of example is products. So the first one of those was found by, well, the function was studied by Euler. So Euler looked at the product, which is usually called now Q infinity, and he proved two things. First, he proved that 1 over Q infinity, is the generating factor. This is sort of obvious, and that's why he was led to introduce this function. It's obvious today that he, of course, had to invent a generating function. It wasn't a fantastic idea. So he discovered that you take partitions, which I want to find out, which I see them. Then the generating function then is 1 over this thing. But the PNs are very hard to compute. And then he realized that if you're a nice formula for Q infinity itself, that by multiplying this nice formula with that and setting it equal to 1, you get a recursion. And you go from there and found a beautiful formula, which is the sum minus 1pn cubed to 3n squared plus n over 2. So I'll explain that formula in a minute. So what it was then found by Dedekind, a century later, that the function a of tau, which is the product of this Q infinity cubed to 124, this one is a modular form of SL2Z, and therefore the 24 power is a modular form of weight 12. And then again, the fact that modular forms of weight 12 is two-dimensional means that automatically, so each time I'm writing identities that these things give, you find that delta, which is 8 to the 24th, is equal to a linear combination of d4 cubed and d6 squared. So again, that gives some explicit basic number theoretical identity. And then the third kind of general construction is theta series, which, well, the simplest example is simply called theta. It's the sum q to the n squared, n in z, because it's a Fourier expansion 1 plus 2 cubed plus 2 cubed plus 4 cubed and so on. So the homomorphic condition I didn't mention here, the growth condition, is just what you see in these examples. There may be a constant term, and there may be positive powers of cube, there are no negative powers. So actually, it's important to us to have a larger space. These are called weakly homomorphic. So here you have the sum, here typically after the expansion, a n q to the n, but I shouldn't write that because the n's don't have to be integers. In the example of APEC has a denominator 124. So in general, these n's are rational numbers with a fixed denominator, but it's in infinite sum with only positive things. That's called strongly homomorphic, and the weakly homomorphic is n is greater than some n0, which can be negative, a n q to the n. And the difference is seen not just at the expansion around q equals 0, but for the asymptotics. Here one can show that this grows up to n to k to an always small way. It grows in rows like n to k, so polynomially, but here it tends to grow polynomially. So while I'm giving examples, let me give examples of this. The simplest example would be, so examples of weak, and I'll come back to polymorphic. Examples of weak forms would be, well, one is the one that I just saw. Here then, q to the n minus the 24th, which is 1 over eta. So that's a modular form of eta half, but it's got one negative power. It's 1 to q to minus 1/24, and therefore p to the n grows like e to the pi squared 2 over 3, the famous Hardy-Ramanujan formula for p. So this is the typical asymptotic product, and another famous example would be if I define the j function. So it's defined as e4 cubed over delta, with the e4 and delta that I already have, minus a constant, which doesn't change. So this is a modular form of 8, 0. Again, it's not a pole. So J is equal to Q inverse 0 because I subtracted the 744 that I would have had, and then some constant integer coefficients. And of course, all mathematicians and physicists recognize this is the famous connection that was found some 30 years ago, the moonshine connection, that it was noticed that this number is one more than the dimension of the smallest irreducible representation of the monster group, and there's this amazing moonshine connection between these coefficients in general and the monster group. So that's just to mention, because it would be important that we have two notions of holomorphic, strongly holomorphic, and weakly holomorphic. It's still holomorphic in the upper half plane, but it's only meromorphic, if you wish, in all of infinity. So now here's an example of the theta series, or more generally, you're going to have theta, or capital theta, I'll never use it again. You have some like this, and you might have a periodic function, I'll ignore that, so I'll just put q to the power q of r, but q to the power q of v, where q is a quadratic form, also with that. And then this classical for the theta series is always a modular form of a r over 2. So for instance, this theta series here is a modular form of a half. So those are essentially the only ones. And then I can continue with my story of identities. For instance, this is the other chart. If I take the fourth power of theta, then that's a modular form. Stop. Theta tells you horizontal. So remember I said that you have, since you have different constructions, but in the same finite dimensional space, you get identities for free. So typical one is theta times the fourth, which is weight 2 on some group called gamma 0, 4. This one turns out to be an Eisenstein series exactly like the ones that we had before, except that instead of d cubed, or d to the fifth, it's simply d to the first cube of the d, and also, because it's on gamma 0, 4, there's a congruence condition that 4 d is not divisible by 4, and so this implies immediately, if you just compare the coefficients of q to the n, then you get for free that the number of representations, counting multiplicity signs and everything, of a given number is the sum of 4 squares. Well, that's just the coefficient of q to the n on the left, and therefore it's a times the sum d divides n before it's multiplied d. But d, that's a famous formula that means, and in particular, it's strictly positive, and you get a one-line proof of Lagrange's theorem that every number is the sum of 4 squares. But of course, it's only one-line proof if you know about multiple forms. So, and soon one more example, if you take data, if you take Euler's identity, which I wrote up there. So I wrote it in the way that Euler wrote it, minus 1 to the n, which is equal to separated n positive negative, q to the 3n squared plus n over 2. But if you write it correctly, from the point of view of the modern period, correctly, then it's a theta series. It's simply q to the n squared. Well, if I should sum over the lattice, I should sum over the positive and negative n. It's even, so it doesn't matter. And here, 12 over n is the standard character to be on 12 over n, which is 1 if n is plus or minus 1 on 12, minus 1 plus or minus 5 on 12, and 0 if it's not prime to 12. So, that's simply a restatement. Again, the proof is one line. I mean, Euler worked for 10 years to prove that he discovered it empirically, and it was very, very hard to prove that that product is equal to that sum. Now we have many proofs. But now it's trivial, because this is a multiform way and a half, that's a multiform way and a half. They're in the same space, and that space is one-dimensional, so they're equal. Well, the constant is used one term. Okay, so now I come to modular forms, and the idea should be that somehow it's a more general kind of object, but it should have the same basic property that if you impose enough restraints, slight conditions, then you get finite dimensional spaces. Is there any kind of eraser? I see these, the hard one, but that won't work. Oh, there's this one. Oh, there's a web. Okay. So, now I want to go to modular forms. And now I'm going to think about 6 examples. So I'll start with one that's actually the first from the literature. And it's a function that I wrote down many years ago, but there was no the definition of the theory of modular forms didn't exist, and neither I nor anybody else thought that this was a typical element of class of function. It's just a function with a cube property, which had several applications, which I won't go into. So the function is called strict h of tau, and this, my first example is using class numbers. And this one's also occurred in physics, but I won't say anything about those papers because I haven't read them and not really say about them. So it's the function which has a Fourier expansion, there's no negative term, and then all the coefficients are integers except occasionally because it's not over 2 or 3, and it happens right at the beginning. We start right out like that. So this is the generating function. Of what are called the Hurwitz-Kronecker class numbers. Which are essentially, well, I'm not giving you a table of the first ones, they're essentially the class number up to some very simple factor, which I don't want to go into. The class numbers of the imaginary quadratic fields, q squared minus n. So these are functions that have been very much studied, that was the names of the authors suggest already at the end of the 19th century. And it was clear from various things, there were many identities that already Hurwitz and Kronecker proved, where certain combinations of h's were coefficients of modular forms. And those combinations were just as if this thing were a modular form, and then if it were, it would have been a modular form weight 3 halves. But it's not. So it's not modular, but it is a weight 3 halves. In the sense that if you apply certain operations to it, which you could do with modular forms, then you sometimes get actual modular forms, and then it only would only have worked if the thing had been modular weight 3 halves. And so what I found, so what you find, is that there's a completed function, which we'll talk about this essay in certain many of you have seen it. There's a completed function which you get by adding to h a correction term. And this correction term is extremely simple. So it's, I think, 1 over the number in front, I think it's 1 over 16 square root. Well, what I've written now is 1 over the square root of tau 2. So remember, tau 2 is the imaginary part of tau, and so you see the strange thing is that the correction term, although it's very simple, in the sense that you can just write it down. There's a function which I'll define in 1 second, a complementary and standard function. And essentially, this correction term is a theta series just like theta. You know, the theta is up there, it's the sum q to the n squared. Here I've q to the minus n squared, so that would diverge. So it's like a theta series of theta to 0, 1. So for indefinite, well, in this case negative definite, we're having forming one variable. But of course that would diverge, but then you put in this function, I have to get the normalization guide, so I have a look. Theta of tau is 1 over 16 pi times the integral from 1 to infinity, u to minus 3 halves, u to minus u to du. And this thing, it's very easy to check, is, well, it's almost enough. The integral, it's little o of e to the minus t, as t goes to infinity. So as a result, this thing is little o of e to the power minus 4 pi n squared tau 2, and then the q to the n term blows up. But it only blows up at half the speed, and so the whole thing converges exactly as fast as it would have done if we had the holomorphic expression. And it's extremely simple, because the correction term, sure, it's not holomorphic, but this is just a standard function. So you're just further expanding with respect to different bases. But the coefficients are 1 if the power, the exponent is a negative square, and 0 in all other cases. So they're extremely easy, unlike, say, the delta, which is extremely complicated arithmetic coefficients. So this is, you should think of this as a simple correction term, but non-homomorphic. So I don't have to think that it's non-homomorphic, it is non-homomorphic. And now the statement is that this thing, sorry, let me first finish the sentence and then ask questions. So the statement which I've yet made, I just said you find this. The statement is that when you make this completion, then this new function, of course it's not holomorphic, but it transforms exactly like the modular form of weight 3 halves. In fact, into the transfer form. Sorry. Somebody? Oh, that's a question. Maybe not.
There are a few misspells.
Sorry?
There are a few misspells.
Can you dictate them?
Big O, I think you need E to be
Oh, here. Thank you. Well, Q might be E. No, Q. Sorry?
And then the next one is O.
Oh, thank you. Well, I'm glad that somebody's paying attention. I'm glad it's not me. So, okay, thanks, Bob. So in modern language, we call, this is the definition, so we call h of tau. By definition, I won't write out, it's not like I will write out the definition. This is modular form of weight 3 halves with completion where I introduce the shadow, or in this case, it's just a function theta. So let me give the general definition. Example, here is. So maybe I make a definition here. I want to be completely precise about levels and so on. Obviously, one can be very precise. A modular form of weight k, and k can be a half-inch, like here it's weight 3/2. So a modular form of weight k is a holomorphic function. H of tau, and I'll use the same words that are there, so they're part of the definition. So it's a triple definition of defining a modular form whose completion of h hat of tau, which is defined as h plus g star, like tau everywhere, where g is a true modular form, but of weight 2 minus k, so g is an ordinary modular form in the usual sense, and this is called the shadow. So now the idea is common. So its completion h hat is h plus g star, is not to tell you g star, but g is a modular form of weight 2 minus k, because you need to curve it's called the shadow. And this thing transforms, well, it simply is a modular form. The conclusion is modular, but of course not holomorphic. And now I have to say what g star of tau is. Well, it's exactly what it was here. If you imagine starting with theta, which is the sum due to the m squared, and then theta star would be this sum. So you see that the main thing is you send the cube minus n, and you insert some kind of an elementary function. And so the complete definition, I can give 3 definitions of g star of tau, and a name. But with physicists, I would only give the name, but instead I'll give 3 definitions. So it's called a non-holomorphic Eiter integral. It is very enlightening if you happen to know what holomorphic integrals are, but otherwise less useful. And then I can define it in 3 different ways up to various constants. I mean, I'm not going to normalize it. One, it's a solution. You see, let's look at this function. If you take data t and you divide it by the square root of t, that just corresponds to replace u by u over t. It becomes the integral from t to infinity of the same of x minus 3x e minus x. So this is just e minus x over x to the 3/2, the root of t. And as a result of that, that means that if you take this function here and multiply it on the left here by the square root of the imaginary part of tau 2, you kill that function. No, you don't do that. If you simply leave it as it is, you think of this 1 over square root of n2, put it inside and think of it as n over square root of n squared tau 2, and then you differentiate. And what you find is that if you simply differentiate in tau bar, this complete thing, then what will happen? Well, this part will give nothing because it's a holomorphic function, so the tau bar derivative. So this is a trick to kill the holomorphic part just by applying the Cauchy-Riemann operator. And then, like what I just said, this thing will be exactly 1 over up to a constant, tau 2 to the 3/2, and then we go to that, which is say tau bar. So that's the relation between the function and its shadow. That's what I mean by saying that the shadow of this function is tau. So you can't define them separately. A modular form is something which has a shadow, which you have to define, and it's in dark, that's why it's called the shadow. It's very hard to find if somebody just gives you the h. But in order for it to be mod, you have to introduce a shadow, and then check that h plus g star is this. So here it's exactly the same story. The shadow, the Eiter integral is defined by the fact that it's non-holomorphic. Its derivative in tau bar times tau 2 to k is equal to the constant times to g tau bar. And you can also define it explicitly, the coefficients right. So if g, let's say for convenience, is no constant term, so g is an expansion, the n cubed to the n, if n is negative then we have n cubed to the n, then it's the sum n positive n to the power k minus 1 times b n bar times, now, as we observed here, it's. So you have to, as I say, take q to minus n, multiply with the same coefficients before with b n bar because I have a bar here. But then you have to change it very slightly by putting in the universal function, and that universal function think everyone knows it's the integral from x to infinity, dts minus 1 e minus 2 dt. So this is standard function, and then it satisfies the differential equation, which exactly tells you that is the same relation will be true in general, the same relation that I had here for any function will say this relation between the completion and the shadow. And finally, I want to put the third definition. So the third definition is.
How is G?
Wait, let me finish the sentence, please, and then answer questions. So it's here I take g of minus z bar bar, so that's holomorphic again. So this is a holomorphic integrand, I can deform as I like. And so up to constants, one checks that this integral is equal to that sum, that they both satisfy that differential equation. So that's the definition. So as I said, there's no way to pick g. If you give me an h, then it's your job to pick g, not my job. You're telling me it's a multiple form, so you have to show it satisfies this definition. A multiple form is always a pair. It's, if I define very mathematically pair, h comma g, where g is a modular form of weight 2 minus k, and h plus g star, where g star is defined like this, transforms like a modular form. But it's easy to see that h uniquely determines g if it exists at all. So the multiple form is just the holomorphic part. And the whole mystery is how you recognize them, because you don't know what the g is. So if that was the question. Well, so I'll be talking about So I didn't understand the question. I'm defining what modular form, so I don't know. But if you ask about strings, then it's not in the place. I think I couldn't hear, but I thought I heard the word string. Something premature. I'm just defining elementary functions.
No, so there are algorithms to determine G for
No, that's what I said now 3 times. There's no algorithm. That's why it's called the shadow. It's very difficult. There is no algorithm. That's why it's the shadow. It's in the dark. Something different. And you don't know what the shadow is. But if they tell you this is a multiple form, it's their job to say it's a multiple form because here's H and G, and then they give the proof. You cannot go from H to G. You can go from H and G to verify these properties.
But you also said it's obvious that it's unique.
That's very easy to prove, but that doesn't help you find it. Anyway, I'm very sorry. Well, my second example, you'll see how difficult it was. My second example shows how difficult this question is. Because the second example, so my first one was the classical example. The second example is the famous Montague functions. So this is the example that led to inventing this definition. So in his famous last letter to Hardy, just 4 months before he died, Ramanuja wrote he was very happy he had discovered a new class of beautiful functions. And he said these are similar to the classical theta functions, by which he meant modular forms, but they're different. And so he gave, so this is a letter of Ramanujan to Hardy, and he gave 17 functions that he called Montague functions, but he didn't give a definition. And he couldn't, because he didn't know about the shadow. That's just the point. It took more than 80 years to solve this problem for these explicit examples. So it's really difficult. I mean, this was 1920, the solution was given in 2002, so there is no simple way. And very good people worked on it. Watson, Selberg, I mean, fantastic good mathematicians, Andrews, Dickerson, there were many very, very good people, but they didn't find the true modular property. So he gave 17 functions with no definition, and the 17 were divided. He gave 4 plus 10 plus 3, which you easily check to 17. And this was called 4 that he said of order 3, but this was also not defined. There was no indication what it meant by order 3, right? No. So there were 3, 5, and 7. Actually, these 5 were actually 5 vectors. And this was one vector of length 3. So here it's actually, and he gave me pairs and here in the triple. So actually there were 5 vector value things and 3, a single vector value thing of length 3. And so let me give you some examples. I'll give you 2 of the 17 examples, just so you see explicitly. All of these were special Q hypergeometric functions. And a Q hypergeometric function, well, it's the definition of this, give 2 examples. So the first one is the sum q to the n squared over 1 plus q squared times 1 plus q to the n squared. So this was order 3 in his undefined definition. So this is for order 3. Now if the denominator had been 1 minus q without the square with the minus sign up to 1 minus q at the end, this would be one of the two famous Rhodes-Ramanujan entities which he and Rhodes had discovered. And those are modular forms, actually, weight 0. But here, he saw that this was different, and he gave a kind of a very partial definition, which I'll tell you in a moment. But he didn't know any modularity problem, so he didn't give the actual definition. And the second one, I'm just giving 2. This is one of these 3. It's actually number 1 of order 7. So if you wish, you could call this F7.1. This is 7.2 and 7.3. And here, sorry, there's, well, if I can write it that way, but then here it's, you don't start at the bottom. You go from 1 minus q to the n plus 1 to 1 minus q to the 2n. So here are 2 examples, and as I say, he gave no definition, but he said that they're like ordinary theta functions with modular forms at asymptotically when q tends to root of unity. Well, he didn't really say that, he just said that q tends to 1 or minus 1. But it's actually root of unity, which if you think of tau, then that means that tau tends to some tau 0, which is a rational number. So if you think of the upper half plane, as you descend to a rational number, the tau goes to e to the 2 pi tau 0, which is the root of unity. So he said, what he meant, so he said, if it were modular, it would transform in a certain way, because you can bring that rational point by modular transformation to infinity, and then use the Fourier expansion. So modular forms, and that was very well known, and he had used it for his asymptotic formulas. So with Hardy in particular, modular forms have a very well-defined asymptotic behavior at these, for instance, when q tends to 1 or minus 1. So he gave an example for f, and he gave this, I don't know how he found it, of course there was no proof given. If you let q tend to minus 1, so I write q is minus e to minus epsilon, and it turns out it's better to multiply by e to pi epsilon over base 4, then you get, well, what he said is you get minus 1 of the square root of epsilon times pi over 24 epsilon. This is exactly like the true modular form of rate 1/2. So if you had the true modular form of rate 1/2, then you replace epsilon by 1 over epsilon, you pick up and plant the 1 of the square of epsilon, and then the new modular form might have a pole, which might be q to the 120 minus 124, and then you get this exponentially large term. So that exponential growth is exactly like we get, and that's the main thing. But now the surprising term is that he said that the next term is 4 plus little o of 1. That's all he said, but actually it's a power series. And the whole thing is a power series in epsilon. And this is not like a modular form, because if it were a modular form of rate 1/2, then you would have 1 over the square root of epsilon. You might have a constant instead of 4, but then you would have some power, now some negative powers over epsilon. You'd have a power series in e to the minus something over epsilon. And so that's not all the same behavior. So he gave some indication. So at least for f, he said a little bit what he meant. He gave a non-trivial property. But for instance, for capital F, he gave no property at all. He just said this is an example. He didn't say what he meant. But I can show you that this is something of computer functionality if you multiply this thing by q infinity. All of them are at most 1 digit. First. So that doesn't prove anything, but at least shows that it's connected somehow to multiple forms, because when you multiply the multiform beta, something with these gigantic coefficients, something is very small. So at least it's sort of reasonable that there's a connection. So now, as I said, the solution to this, and that's exactly answering your question, sorry to insist so much on it, it's difficult. In 2002, some mistakes in my doctoral student, I'd asked him to study my theta function, maybe try to find some new identities. I certainly never imagined that he could solve the more than 80-year-old problem that many people had asked, what kind of multiple behavior do these things have? But he found that all 17 are multiple forms, and he said the definition above of weight 1/2. But he proved it basically 3 times. Well, for most of the functions, 3 times. He gave 3 approaches, which I think all 3 work for all 17. He didn't check all 51 cases. And so what he showed is that Ramanujan's data functions, Ramanujan's data functions, are contained, well, actually the intersection of 3 classes, which are my next 3 examples. I told you there are many constructions of multiple forms. So far, I've picked 2. Q hypergeometric series. I never said what Q hypergeometric series is. It's a series which looks like that, which means that the nth term is just the product r of q times r of q squared up to r of q at the end, where r is some fixed rational function. So those functions are examples. So, but Zagier showed that he didn't prove that part. This he found in literature. He discovered that if you looked at the many, many papers by the people I mentioned, Andrews and Hickerson and Walton and Selkirk and all the others, then they had proved many identities. They just didn't have the modularity property. And the identities you could group into three groups, that each of the modularity functions, many of them, could be seen as special cases of three classes. One is a very special kind of infinite sum called Appel-Derk sums, because they were discovered by Appel around 18, well, Zagier found a paper of 1892 of that, Czech, but then they were also discovered about 5 years earlier, independently by Appel. So that's a very specific kind of sum, and various identities, I'll give an example in a minute, show that then all of Ramanujan's theta functions to be related to these Appel-Derk sums. The second kind is indefinite theta series. So again, I'll give you an example. So that's like the theta series that I had in the top board, except that the quadratic form Q no longer is positive definite. And finally, and that's the one that's going to be most interesting for our application, Fourier coefficients of narrowmorphic Jacobi forms. So now I have a lot of things to define. It's a slow process. I guess I can use the sideboards for that. So let me start then with each of these classes. So let me start perhaps with the Appel-Derk sum, especially if I can find that seems to produce my notes in some horrible way. Then you actually remember it, so I can just write it. So Watson had proved an identity for f, so I started with 1 in order 3, which is still written on some board up there, the top. And he showed that if you multiply it by q infinity, then you get the sum, I think it's 2, I have my notes somewhere. If I remember correctly, it's 3n squared plus n over 2. That would be exactly like Euler's formula, but then you divide by 1 plus q again. So that's the typical, if you compare this with the formulas which Zagier is still not erased, of my two special constructions, there were two kinds. One of them was a sum of, it's called the Lambert series, there. It's a sum with the form q to the n over 1 minus q to the n, 1 plus q to the n, or something like that. So if I didn't have the numerator, this would be like an Eisenstein series. On the other hand, if I didn't have the denominator, well, in this case, I would exactly Euler's formula, which is still here, minus 1 to the n q to 3n squared plus n per 2. And that after a factor of q to 1/24, which I did here anyway, is a modular form. So this is kind of a hybrid, and so this is a typical Appel-Derk sum. That's what they look like. So they all look exactly like that. You have a quadratic form in q in the numerator, and a linear form in q to the n in the denominator, very roughly. Okay, so, and then what Zagier showed, so he found that many of there were identities already published, that many of Ramanujan's functions, like Watson had proved this identity, were of this form, and so he proved the general theorem that these Appel-Derk sums had the completion in the shadow, as I gave before. I'm not going to go into the details, but maybe I should say in this case, so in this case, that means, so this is my work of some favorites, it deduces from this identity the following factor that if I define, I'll call it H3 to remind you that it's order 3. If I define H3 to be FQ, excuse me, this is FQ because Ramanujan always wrote as a function of Q. But now I know it's a function of tau, and I have to include a factor of q to minus 1/24 to make it good. You already see that in the asymptotics. I don't know where they've gone anymore. Over there, yeah. I had to multiply e to the plus pi epsilon over 24 times f to make it work. So this is the good function. And this one is the multi-modular form. So I'll use the double n. So this is a multi-modular form as I said in way 2, and its completion. Well, of course, it's h3 plus something, and it's exactly the same function now that we had before. So it's, what I can write now is the sum, here's one way to write the sum n over 1.6 sine of n, and then this incomplete gamma function, 4 pi n squared tau 2, but then it's over 24, because here it's minus n squared over 24. So, and the shadow of this is then the same thing, where you drop this, and you, so the shadow will be the same sum, n over 1.6, and then will be n times cubic plus n squared over 24, which is some other classical theta series of 3 halves. So that's an example. So, I mean, this is not at all trivial. That was one of the chapters of this thesis, which showed that Laplace sum has associated to it just by the structure of the sum. You can guess in that case what the shadow is, and then you take the Eiger integral t. Of course, it wasn't known that that's what you have to do. And when you add it, it transforms like a modular form. So here this is a modular form, grade 1 half, non-homomorphic, act on the full complex of gamma of 2 and not 3. So the order of 3, whatever it was, is very strange. Okay, so that's the first example, and such examples occur in physics, and maybe I should say that, I don't know, maybe I'll finish the examples on the mathematical side and then say where this comes in physics. So that would this kind of thing, I can't have that. So then the second one is indefinite theta series, well, it's the fourth one in my numbering, so it's still written up there. Indefinite theta series, again, there's an example. So it was an identical value in literature, very difficult identity, proved by Hickerson. We said that the F that I had above, which remember was the first of 3 of Ramanujan's multiple forms of order 7, whatever that means. He showed that if you take this and you multiply just like lots of Q infinity, then it becomes a theta series. But it's the following theta series, it's a sum over R and S, I have to leave a little space. Now there's a sign, so now in the theta series. And here's with 3r squared plus 8rs plus 3s squared plus r plus s, the whole thing divided by 2. Now that would be a perfectly good theta series like I wrote and gave you in my lecture, except there's this stupid shift with the linear terms in the exponent, which I'll correct in a second. But this form is not positive definite because 8 squared is bigger than 4 times 3 squared. And so you can't sum over all r and s because it would be positive. You can sum over the positive quadrant, but then turns out you also have to sum over the strictly negative quadrant and subtract that. And then that was the identity that Hickerson found. So it's some kind of an indefinite theta series. And you can write this then more intelligently if you take, let me get the normalizations right. So a more intelligent way to write it would be if I define H71 of tau to be equal to q to the minus, again we have to put it in the appropriate power, which in this case is q to the power minus 1 over 168, then what this says is that it's 1 over a to tau times the sum in I of r and s, but they're both not in z anymore, but z shifted by 1/14th, and then I have minus 1 to the power r plus r minus s, which is an integer, so that makes sense. Here I have sine r plus sine s over 2, so that's 1 if they're both positive, 0, minus 1 if they're both negative, and 0 if they're opposite side, so that's just this term. This is minus 1 to the r minus s, and then the last term now is much better, because I've just shifted r and s by 7, and so now it's become really homogeneous, as it should be for programming form. So that's absolutely a theta series, just like the usual classical theta series, except for 2 things. First of all, there's the sign, and second, it's an indefinite form. Of course, they're related, otherwise it wouldn't converge. And then the statement was, again, that, so that's a very difficult identity of Hickerson. But then, again, some of his papers show he invented the theory of how indefinite theta series of this type transform, and he showed that this implies that this is what the following says. I define the completion this time as H7 plus before, so it's the sum 1 over pi squared of pi, sum n conquered to j modulo 7. So j, well, sorry, this is nj. Let's say 1, 2, or 3, but actually you can take any j mod 7, it's an odd function, so there are only 3 of them. So I take n conquered to j modulo 7, and then you take the same characterized by the n that we already had, sine of n, this was before, the same gamma function, half 4 pi n squared L2 over now 168, I think, and then Q R minus n squared over 168. So here the shadow will be the same, the sum over all n in pi of n times Q to the plus n squared over 168. So that is now a modular form of something, and here I can tell you about this, and this is important for what we're going to do afterwards. Namely, I already mentioned that none of those examples, except the first ones, they were all vector values. The ones order 5 were vector length 2, this was vector length 3. So this individual thing is a modular form on some horrible subgroup, very large index subgroup. But as a vector, it's a modular form of L2Z, because under translation, it's very easy to check that it just transforms by 168 for Unity, which is, if I remember correctly, 6j minus 1, 6j plus 7 squared over 6j plus 7 squared. So under translations, each of these functions is a constant, a scalar, but under inversion, you get the square root of 2 times the square root of tau over 7i times the sum k from 1 to 3 of sine of pi jk over 7, if I remember correctly, the 6 over 7 times h 7k.
That's on h hat.
Well, thank you very much. That would indeed is not true unless you hatify it. Here, of course, it's true with or without, because that's triviality. But the other, of course, is the thank you very much. Okay, so here we see also, and this will be very important to us later, the fact that these things come in natural way in the vector value thing. And so the next one, oh my gosh, the time is, this is not possible. Most of the time is gone, and I've done 1/6 of my notes here. Okay, so I was going to give a review of Jacobi forms, since I gave a review of modular forms, but I now see that I can, so I'll just tell you in a few words, because that's actually crucial now about Jacobi forms, and also for class application, black hole state mapping. Oh my gosh, all the things I prepared. So carefully, I shouldn't use slides. Okay, so we have the generalization of modular forms, which are called Jacobi forms. These are functions of two variables, tau and z, as I wrote at the beginning. And they will be periodic, so they'll have some sort of expansion, q to the n, y to the r, and they satisfy two properties, a modular property, which is similar to the one before, except that the z also gets changed. So you have the same z plus e to the k. Before this is called the weight, but before this is called the index. And now that comes in as e to the 2 pi I times mc. The exact form doesn't matter very much. Doesn't matter. Not for now. And it also satisfies, so this is for A, B, C, D, and SO2Z, full of. And then the other is if you shift by the lattice generated by 1 tau, then you pick up the function minus m r squared. Tau minus 2m r. No, whatever I did. Q minus m r squared minus 2m r times 5 times. So this property we call Jacobi-like, that we call elliptic. And so you can check rather easily that 1 is equivalent to saying that phi is an expansion, psi 0 up to some constant limit, then psi 1 plus a multiple of psi 0 times e squared plus psi 2, psi 1 prime, psi 0 double prime. Is equal to 4 and so on, at least for k is even, where psi j is a modular form of weight k plus 2j. And 2 is equivalent to the fact that phi is an expansion as the sum. Well, first of all, you check easily just by substituting this for the expansion into that c of nr is equal to capital C, let's call it the determinant, for n minus r squared. And r, of course, that's a triviality, that just changed variables, if I use that. But now if I use these as new variables, then it becomes periodic in r. So they're only finitely many collection of coefficients C of delta. So here we have C of delta, and then the second argument is only finitely many deltas. So that's equivalent, and that is again equivalent to saying that phi has an expansion as the sum L modular 2n of some power series in tau alone times the standard theta series in two variables. So this standard theta series, A and L, is just the sum of all n HL is just the sum of C delta L cubed to delta before. But here you simply have n greater than weakness, so that's called weak, and then they're weakly holomorphic. And, well, sorry. And then for this one we showed that this thing, just like in the classical case of non-conformity, it's a very simple algebra found to be generated by 5 forms, E4 and E6 as before, A, B, and C with one relation, 432C squared equals BA cubed plus some important polynomial A and B. So this ring is infinitely generated, this one is finitely generated, and the A, B, and C are functions which have occurred certainly many, many times also in physics, and they're so important I'll actually write them down. So it's theta tau z. The first one is theta tau z squared. It's the classical probability function. I want to write it down. The function b you can write in two ways. You can write it as 4 times the sum. You can take the three, there are 4 Jacobi theta functions, but one of them, theta 1, which is theta, vanishes at the origin, but the other is done. And so you can take this thing. So this A is a Jacobi form, weak Jacobi form, A minus 2, index 0. This has weight 0. Oh, sorry, index 1. This also is index 1. It's also B. And finally, C is simply theta 2z divided by A tau cubed. And so that one is B of weight index 2 with weight minus 1. So you have these three kind of basic forms, and they generate the range of all of the forms. So now, what Zagier found is that if you take, so as I just explained, if you have a Jacobi form, you can expand it into some of theta series, and then the coefficients of that, I didn't say that, but it follows easily. Those HL up there are modular forms, ordinary modular forms, of weight k minus a half, but in fact they're vector valued because you have a bunch of them, 2m of them. So that's like what we had before. So now what he discovered is if you take meromorphic ones, then you have to do something, and he described it in certain examples and gave it kind of general here, but not a very precise one. He gave with Rotian double copy of a much more precise version. There's a canonical way to split meromorphic Jacobi forms, the good ones, into 2 pieces. So one of which is modular form, and the other is actually not down there somewhere. So what you find is that if you have now a meromorphic, I'll put capital MER, meaning that the poles don't move. The pole is at the fixed torsion point, like tau plus 1 over 3. So if you have this, then you can write phi canonically as a sum of 2 pieces. The finite part and the polar part. And the idea is sort of important, so let me say, if we were in the classical case, and I take this expansion which is here, then you would see immediately that you get the coefficient h of tau, which remember in that case was an ordinary multiple form. And I take it off by definition. It's the Fourier coefficient. So you would look at this integral, and it wouldn't, because it's holomorphic, it wouldn't matter where you are. But now, because the play is poles, there's a wall crossing phenomenon. That's why this comes up in counting BPS states and the like. There's a wall crossing phenomenon. It depends where you count. So in the classical case, this is periodic in L, it's independent of the path, it's independent of Z0, and it's modular. Here, all of that fails. What you can find is if I write down what the Z0 is, or for generic Z0, then it's easy to see that if I change Z0 plus 1, nothing changes. But if I change Z0 plus tau, I change L to L plus 2n. So in the holomorphic case, where it's independent, it was periodic. Now it isn't periodic, but because of that choice, I can make a canonical choice, which is I choose for Z0 a number that depends on that. This corresponds to the factor contour that physicists use. So you take the same integral that I wrote here, but in that particular mode. And then you define phi f as the sum HL of tau, theta n tau. So now these are now well-defined things, and they're periodic. Because I set it up, it's periodic. So I can make an expansion just like before. And it's a theorem that we prove that the HLs are not modular forms of usually represented k minus half. So you get a thing, and this is therefore what we call the non-Jacobi form. So that's what we change. So that's the finite part of the thing. I'm assuming that Km are the same as they were before. And this one, the other part, the component part, is an explicit up-down sum, which I want right now. So you can do this all completely explicitly. So now I want to say something about the application in physics, but I meant to say something about where the up-down sums originally occurred in the work of Eguchi, Taubina, Oguri, and Yang in 1989, connected with superconformal characters and superconformal algebras. And that's taken 5 minutes, but I want to have them. So I'll skip that and go to the one that we worked on, the application that came up with black holes. So I'll have to be very brief on that. So let me say just very briefly how it goes. So let me give just one really nice example. So first of this thing. So let me define phi 1, 2, 1 to be b squared over a. Actually, I choose b squared over 144a for some reason. So b and a are these two basic Jacobi forms which are here. So if you work out this thing, then you find out it has some rather unpleasant, rather huge Fourier coefficients. So this has an expansion. Well, the finite part, I call it capital Fourier, the finite part, has an expansion just in the form that any Jacobi form would have. Here it's x1, so it just depends on 4n minus r squared. And the ends, here's these coefficients, c of delta and c of delta here. The coefficients are minus 1, 0, 3, 4, and so on. And the coefficients you find are 1, 22, 152, minus 636. So there's some huge number, very ugly, when you do this finite part. But now, we can change this by an ordinary modular form. This is weight, no, it's what I said, weight 2 in x1. Then I can take A, which had weight minus 2 in index 1, and multiply by E4. So that's just an ordinary modular form, so it's holomorphic. It doesn't, sorry, it's also, that's true, it's a weak form, so it also has a negative form. And its coefficients, I'm making the traces of the J function, so I mentioned that, are like this. Now if you take the difference, so this is another example, if you take the difference and divide by 288, and here you get 0, 24 over minus 288 is minus a 12, this is a third, this is a half, and so on, and you get exactly the function h that I started with. So the class number example occurs in this extremely simple way, and here, well, I didn't quite define this, but remember, it's the finite part, so to define it, I just have to tell you what the polar part is, and that's a very explicit sum. It's the sum q to the n squared, right, the 2n plus 1 over 1 minus q to the n minus squared. So exactly this kind of decomposition came up in the work of Eguchi, Taubina, that I already mentioned, in connection with the decomposition of superconformal algebra. So there was a similar splitting into two pieces, which I was going to describe. So this is sort of typically how it works. And now remember that our examples, Ramanujan's examples, were always vector value. So for instance, if you take the example from that paper of Taubina, etc., that I've now mentioned several times, you get a famous modular form, or the modular form, whose first coefficients are 45, 231, and so on. And this is the one that was discovered 2 years ago by Oguri, Eguchi, to be related to there's a monster, another moonshine story, the material group M24. So this is a very famous modular form. And then you can make out of this a form which is exactly, you get it in the same way as this. You get the Jacobi form, in this case of weight 1 in x2. And similarly to the Ramanujan example that I gave you before, remember I had the H7J that I told you of tau. If you put theta 42 on J. Tau Z, and the same character kind of for J could be used several times, and this one turns out to be a multi-Jacobi form at the index 42, and simply these order flight examples at the index 30. So we find the number of the order is 6 with the index. It's kind of a little unexpected. So you have these simple classical examples, and now just to end the story, since my time is running over, let's run out. In this program of counting BPS states for quantum strings, for quantum black holes, you, again, and that is already known, the corresponding multiplicities of certain non-order BPS diagonal states, I can't go into any of it, but you have a Ziegel multiform, the famous Ziegel plus form phi 10. It's a Ziegel form of degree 2, so it's an expansion of Jacobi forms, but you have 1 over phi 10. And so you expand this Ziegel form, the Ziegel variable, as a tau to Z and the third variable, and so you can expand this as something with E of n times the new variable. And then this thing is a meromorphic form of weight minus 10, because this is minus 10 and index 10, but it's now meromorphic. And so we can play this whole game, and so when we do that, we find that you can split it up into sort of canonical pieces, and you get an extremely interesting family of modular forms of weight 2 and index 1, and there's a very similar definition of the family of index 1. And now this family includes all of these classical examples. So each of these examples I've given, the class numbers, Mathieu and Munstein, and all of the others, turns out to belong to this special family, and there are, well, we have 3 or 4 main theorems given appropriately, but since I've completely run out of time, I think we better skip them, hope somebody asks. So thank you very much.
Yes, so speaking of those 17 forms, has it been proven that it is just those 17 and nothing else? Because if they're like a
No, not at all. First of all, what is it? His letter only contains 17. There are many more. Already Ramanujan himself found about 20 more that were found later in his notebooks, and some others were found. It's not well defined. Do you mean which geometric series are modular? Is that your question?
My question is, why are those 17 so interesting?
Because he wrote a letter. I mean, this is like he wrote a letter and he gave 17 examples, so we won't explain them. But they're only the 17 that he listed. There's nothing, those are just the ones that he defined. And for 82 years, since there was no definition, the definition of a log theta function used to be, it's one of the ones in Ramanujan's letter, or in his lost paper. I mean, there wasn't a definition, now there is. So if your question is, are there 200 geometric series which are modular? Infinitely many. In those even for modular forms, this is a very deep conjecture. I can't go into it. Not conjecture relating to algebraic K theory. Nobody knows how to classify even the classical modular forms which are represented as 200 geometric series. So that's, in a sense, that's the least natural representation, because we can't prove any of these properties directly. So it's just a historical, it's just a letter, historical letter.
And also, what does it mean for the 3 or the 5?
I told you that he didn't define it, and that now, because of what I just said, we now find that these order 7 things correspond to index 42. These order 5 is index 30, the order 3 is
actually people in order 7 instead of order 8.
Yeah. Yes?
You give examples with a modular form is 3.5 and 3.5, with shadows where there's 3.5 and 1.5. Is there any relationship between these two different ways?
Sure. So I didn't define. I said that Ramanujan's functions are called, we call them log theta functions because he called them that. But there's no definition that I gave in my talk on this. A log theta function is a modular form whose shadow is a unary theta series. Unary theta series means just q to a single variable squared with maybe a polynomial in front. And it's very well known, kind of trivial, that unary theta series, there are only 2 kinds. You have some periodic function times qn squared, or you have n times periodic function. Character. And this times grade half, and this is grade 3 half. So the shadows, by definition, the log theta function is one whose shadow is a unary theta series. So it has grade half and 3 half, and therefore since that's 2 minus k, all log theta functions have 2 halves or 1 half. So the particular family I told you that we studied once where with phi, I'll just do it for phi 2n, then HL, the shadow, is simply you take the associated data series and you set z equal to 0. It couldn't be anything simpler. In the case of wave 1, it's the z derivative. And those are the only two you can do. So all of our examples in these families are about theta functions. And all about theta functions automatically obey the half to 3 halves.
Right.
The converse isn't true.
So the shadows have a simple relationship, but the modular forms also have a relationship.
No, there aren't running into each other. There's only one. There aren't two to relate. We have one multi-modular form. I'm just saying the definition of a multi-modular form is called a multi-theta function. If every multi-modular form is a shadow to an ordinary modular form, this is multi-theta k, and this is ordinary where 2 minus k by definition. So if this is a unary theta series, then we call this a multi-theta function. But all unary theta series obey the half to 3 halves, so all multi-theta functions, and all of our examples, and all of our Ramanujan's and all the classical ones, class number and all the others, are multi-theta functions. But there are plenty of multi-modular forms that aren't. So I'm not quite sure.
I guess what I'm asking